Hello everyone. We are the Next Generation Design Alliance, a group of 5 mining engineering seniors. Our team was contacted about conducting a pre-feasibility study for a copper deposit in Arizona. The investors want to know the viability of an operation focused on dump leaching as their method of extraction. The project given to us was a design project that put together many skills that have been acquired over the years from our curriculum. The division of work involved dedicating each member to a specific part of the project in which we felt would best maximize everyone's strengths and involvement. Going from left to right, Damien was involved in the design of the open pit, as well as creating production schedules for different scenarios. Francisca was responsible for all the financial aspects of the project. Sarah worked alongside Damien for the pit design and scheduling. Israel was responsible for designing the dump leach method and looking at different parameters to maximize extraction efficiency. And not pictured is T, who was responsible for all the permitting as well as putting into effect a closure plan. In terms of location, the project is located 28 miles southwest of the Globe Miami Mining District, on a mountain known as Grayback. The closest community is Kearney, Arizona, about 12 miles away.
Moving on to the mine design and production schedule. Here's the original topography, and here's the Lurch-Grossman optimization. The algae model created led to the identification of 4 areas of interest. Here's the LG overlaid by the block model we created for acid-soluble copper. It was calculated using drill hole data based on the inverse distance weighted method of interpolation. Of the 4 areas identified, Phase 4 was deemed unminable due to the narrowness of economic material. The other 3 phases continued on to the mine design portion. We used the following parameters to design our pit limits. Our design was limited due to the fact that data on rock strength, lithology, and faults and contacts was not known. Clio is the most centrally located of the phases. It was selected to be first to be mined to provide clear access to the next 2 phases. Frida is directly south of Clio. Frida is the most complicated of the phases due to the nature of the switchbacks required. Last but not least is Joan. It is slightly separated from the previous 2 phases by a narrow valley. A fill road will be constructed using waste material to provide access from Clio to Joan. Here is a summary of key information regarding the 3 phases. The production schedule was created using a production target of 20 kilotons of ore per day. This created a 10-year mine life. Leaching operations will continue 10 years after mining is complete.
Now we move into mineral processing, a key stage in project codename. The following graphs show an exponential decrease due to the same underlying leaching behavior over time. This graph shows the sharp drop because reactive minerals dissolve early, requiring less acid over time. In this graph, most of the valuable metal is recovered early, fewer resources that's needed later, making long-term leaching more economical. And this graph confirms that most recoverable metal is extracted early on, with diminishing returns over time. This flowchart outlines the process from blasting to dump leaching. Sulfuric acid is sprayed over the ore, creating a pregnant leach solution called PLS, which is collected and sent to solvent extraction. There, copper is chemically separated and turned into electrolytes, which are then processed through electrowinning, where copper plates onto steel sheets over 10 days to then be separated from the steel sheets, weighted, and be shipped ready for consumers. Lastly, this flowsheet adds detail by showing material reuses and a more thorough explanation of how the process goes. For example, the organic phase in solvent extraction is treated and recycled, and the raffinate is returned to the leach pad, improving efficiency and sustainability. As for the leach pad, it is designed to hold 37.87 million tons of ore. All the details are shown on screen.
We then evaluated the project economics using a 20-year life of mine cash flow model based on the final pit design in order to determine whether this project is feasible or not. A 20,000 ore per day production schedule is created specifically for this purpose. As we can see here, although the mining ends in year 10, the leaching operations continues through year 20. Copper productions and sale increase gradually over the first decade before declining significantly. As for the economic viability, several critical variables were considered in the model. All of the assumptions are provided on this slide. Using the base case scenario, we then generated the cash flow profile as shown here. So we can see the cash flow is predominantly negative, especially between year 6 to 10 and year 12 to 16, not to mention the first year itself. Hence, the breakdown is then looked at to help us identifying the key factors contributing to these issues. As depicted here, the net revenue for the project fluctuates between negative $20 million to $60 million, peaking in year 12. Despite this apparent upside, initial capital cost still presents a significant barrier. Approximately $220 million is required in year 1 for development. In addition to that, the other expenses also make the cash flows seems to be worsened. Unfortunately, the projected revenue is insufficient to offset this cost, which then led us to ongoing negative cash flow, specifically in the area marked on the slides. The next slide presents some of the major equipment considered for the operations. Moving on to the sensitivity analysis, we performed the analysis on copper price, capex, and opex using 5% incremental change and 1% for discounted rate. And we found out that copper price emerged as the most influential factors. However, even under the most optimistic conditions, the project still results in a negative NPV. In summary, the project yields a net present value of negative 380 million and an internal rate of return of negative 52%. This value definitely indicates a substantial economic loss, rendering the project unfavorable for investments.
And now we move on to the environmental closure activities as a part of the feasibility of Project Codename. Environmental and reclamation planning ensures responsible mining, protects ecosystems and communities, and enables safe land restoration after closure. Located just miles from the Gila River, the proposed site sits in a sensitive desert ecosystem. That's why our environmental strategy begins with baseline studies measuring air and water quality, climate patterns, and local biodiversity. This will help establish a robust understanding of the existing environmental conditions to restore in the future. Identifying several threatened and endangered species near the site, their protection is highlighted in this feasibility study, with mitigation strategies including habitat preservation and careful monitoring throughout the life of the project from exploration to closure activities. Engaging with the local community and tribal nations like the Gila River and San Carlos Apache tribes ensures the project not only meets regulatory standards, it respects the people and the history of the land. A $41.5 million reclamation plan will begin during operations, including native plantings, erosion control, and long-term monitoring to restore the land for community and wildlife use.
The NPV and internal rate of return yielding negative values makes the project unfavorable in these conditions for proceeding. The poor return on investment was something that initially conflicted the team, as we all wanted to see a successful project unfold. However, this result is something that is common in the industry. The team recommends to reinitiate the feasibility study to include processing of sulfides and looking into costs of a milling operation.